I'd like to acknowledge also my colleagues who, in this presentation, we will go through some 3 examples, and my colleagues Annette Schaefer and Jeff Sondrup, who worked extensively on those. Okay, our outline, just introduction and background to the INEL to familiarize yourselves with the site. Current modeling approach, our general philosophy and how we approach modeling. That will include several things, this track 1 and 2 process, and some other aspects. I want to also focus on the difference between the PA process and CERCLA, and primarily we have different questions we're trying to answer. And the models really get fundamentally different because we have different questions we're trying to answer. And then we'll go through these case studies, the radioactive waste management complex and what we call the waste area group 7, RIFS, that are connected, where we pretty much used information from one or the other and tried to integrate them so there was consistency between the modeling approaches, but there's some problems with that, just because of basically a different question we're trying to answer. And then some summary and conclusions and suggestions for ask them. So the whole thing really started in, well, INEL's been around since the 40s, but in terms of environmental restoration, 1989, INEL placed on the NPL list. And then by 1991, we had an agreement between the DOE, EPA, and state of Idaho as to how to address the cleanup and of the sites and corrective actions. The site we separated into 9 waste area groups, and we performed risk assessments on all 9, and these roughly correspond to the INEL facilities. 10th one was identified that included the Snake River Plain Aquifer, and then a record of decision has been completed on all of them. So to a certain extent, we are done in Idaho. Here's the waste area groups. The pointer here. Up here in the north is called the Test Area North. That's, I can't read it, WAG 1. And then we have the NRF is here. Our advanced test reactor that's currently operating is over here. INTEC is over here. That's a Idaho Nuclear Technology Engineering Center. And then we have the old Argonne National Laboratory had a site out here they call what MFC now, and CFA, and then the RWMC down here. And there's a number of other small ones. PA and composite analysis have been performed for 3 facilities. The radioactive waste management complex, that was, the first one was completed in 1994. We had a technical revision in September 2000 and a second revision in 2007-2008. And then we had the Idaho CERCLA disposal facility. That's a licensed CERCLA disposal facility, but we ran it through the 435.1 process. And then the tank farm facility, PA, that's our waste tanks that have been stored waste, and these were emptied and grouted and closed up. And that was, April 2003. I'm going to focus mainly on the RWMC and the ICDF, mainly because this was the only PA that was contracted out to be done. All the rest have been done in-house, and most of the CERCLA risk assessment's been done in-house. I want to stress one thing about doing everything in-house is we have kept the same people involved with this for years, so there's a wealth of institutional knowledge that is transferred throughout these assessments and can carry and have been carried forth in terms of our understanding of the system and how they're approached. The active low-level waste disposal site at the RWMC is being closed, and a new facility, who said, was it John? John talks about being able to do a PA from the start of a new facility. Well, here it is. We have one to do right from the start. It's in design phase, and we are in the process of doing a performance assessment for that. And then a revision to the ICDF performance assessment has been completed, is currently under DOE ID review. Here's our low-level waste facilities. The ICDF is up here at Intech. Tank Farm is roughly up here, and down in the southern part is the RWMC. Just for perspective too, groundwater flow in the Snake River Plain aquifer is generally this direction. There are some differences. We'll show some slides there with flow paths and whether or not you're in the direction of it. That's important for composite analysis. So our general approach to PA/CA modeling and CERCLA risk assessment is a top-down approach. Simple models, conservative assumptions, used first to identify important radionuclides or chemicals, and I'll talk a little bit about the track 1 and 2 process we implemented for CERCLA there. Essentially, if all radionuclides and chemicals are screened, then no further action was taken. Then what was left, we developed a more detailed conceptual site model and more complex models depending on how severe the problem is, are developed. And finally, the final model used for compliance demonstration usually represents some meld between the complex model, what we gain from the work and our understanding doing the complex modeling, and a more pragmatic approach to where we have to produce n number of runs for n number of contaminants. So it's essentially model abstraction. There's several different ways we've abstracted models. Track 1 and 2 process, I would have to say, is one of the most successful ones I've ever seen implemented, because we were able to reduce the number of sites we had to look at with agreement both from the state and EPA Region 10 with minimal effort. Essentially, we established a screening methodology with concurrence from the state and EPA. In fact, we sat down in an office in Seattle at EPA Regions with a giant box of, what was that, chocolate-covered coffee beans, and we hammered out a methodology we were going to do, including parameter values, and that has worked very well in terms of addressing many, many sites, because I can just go to any of the state or any of EPA. They say, oh, track 1, 2, okay, boom. I see what you did. I agree with it. Very conservative parameters, but it works very well for cutting the problem down to something we can deal with, and it really pouring our efforts into what was really important. The overall methodology included both models, computer codes, and site-specific default parameters, and really almost a conceptual model. Our conceptual model was quite simple. Flow through fractured basalt is instantaneous. Flow through sedimentary interbeds takes time. And that conceptual model has proven to be true in a number of field experiments and also detailed modeling. And so many of the decisions made here were based on the track 1 and 2 process. Okay, differences between CERCLA, RIFS, and performance assessment. Now, well, first, our RIFS is really calculate risk and evaluate cleanup options, which is probably an important part of it. Our PA is just to demonstrate compliance. Those are very different assessment questions, and really they can use the same models, but the models are really applied differently to work towards these two objectives. Health endpoints, RIFS is carcinogenic risk or hazard quotient, MCL. PA is radiological dose and MCL. There is a critical difference here when you deal with this aspect of it and rapidly moving contaminants, and that is the carcinogenic risk is computed over a 70-year or 50-year, 70-year lifetime. This is computed on an annual basis. So what's more important here is the integrated amount over that period. What's important here is the peak. This is more with rapidly moving contaminants. So this is really, we have a different endpoint in this sense, and I'll pick out several examples also in just the PA where we come up with different contaminants that were important. Data, RIFS, is data rich in terms of radionuclide and chemical concentrations in the environment. You've got existing contamination. Ideally, PA's doing it before the facility built. We may have lots of characterization data, but we wouldn't have contaminant concentrations in the future. We're talking about a prospective analysis. So there is very little data in which to really calibrate or even validate the model. And our time frames, RIFS is retrospective and prospective, so we're projecting out. PA ideally is only prospective. Now, of course, the first example I'm going to use is really a retrospective, more of a reconstruction, because we had so much past disposal history. So our first case study is the WEG-7 RIFS and the Radioactive Waste Management Complex Performance Assessment. So as I showed, the RWMC is about 70 hectares in the southern part of the INEL. It began receiving waste and disposing in unlined trenches in 1952, and their disposal practice there was basically line the drums up and put a D9 cat, push it in, and then drive over them, make sure they're good and crunched up, and then pour dirt on top of it. So obviously we don't have a lot of anything to mitigate the release from that, and that had to be accounted for, so it became more of a dose reconstruction project in that sense. We also have TRU and mixed hazardous waste from Rocky Flats. That's carbon tetrachloride and plutonium. The low-level waste only disposal began in 1984, so now we have this active CERCLA site where we have an active also low-level waste disposal site. Currently, the low-level waste has been limited to just remote handled waste and soil vaults, and disposals are slated to cease in 2015. So here's what the RWMC looks like. It's kind of a hodgepodge. Here's what they were currently actively disposing in, and this is what our performance assessment dealt with, just with this particular site. For the RIFS, they had to deal with also the waste in all these other unlined trenches and pits. There was a especially nasty one up here called Pit 9 where they're actually retrieving the waste. And the soil vaults are basically like large cylinders drilled into the soil and basalt where they handled low-level waste. It's a unique, I call it a unique site setting, but then again, almost everything's unique in that sense. but it is an active low-level waste disposal facility within the CERCLA cleanup area. And we have not only the RADs, but the non-RADs, the chemicals to deal with, and inorganic like chromium and nitrate, and the plutonium from Rocky Flats. Retrieval of waste is currently ongoing, and also vapor vacuum extraction of carbon tetrachloride. So in doing the performance assessment and also the RAFS, we had to account for the fact that waste is being continuously disposed, or being disposed at the time, because there were releases occurring before the end of the simulation. Typically, you might start with some initial condition. We dispose some 500 curies or whatever of a radionuclide and then start a simulation. Our simulation had to progress while we're disposing, increasing our inventory, and releasing at the same time. So this came into, there was quite a bit in the way of source term modeling. The CERCLA risk assessment model, we had the three-dimensional tetrad model for flow and transport. There's the model domain of the Vadose zone. It was linked or coupled to the saturated zone, and Jeff, correct me if I'm wrong on any of this. Jeff did a lot of the modeling. One of the key aspects to this too was a low permeability zone underlying the RWMC. Originally, this model was really made to, one, understand the carbon tetrachloride plume, and also design the remediation of that, the vapor vacuum extraction. So in this sense, we needed a model like that to address those issues. In the surface, the source term was decoupled. We used the dust model to predict, with a number of modifications that looked at container failure rates, infiltration, and different waste forms, including activated metals, resins, and miscellaneous trash, which was a large part of the source term. Yeah, diffusion out of sludges, and also diffusion out of beryllium reflector blocks that had large inventories of tritium in them. And so there was a lot of detailed modeling. Basically, we addressed it with detailed modeling that was then abstracted into the big model, in the sense of we took the results of that and put it in the model. For example, the beryllium block modeling, we did detailed calculations of how fast the beryllium would corrode and release tritium. We also looked at diffusion of diffusion of tritium through the beryllium, and came to the conclusion diffusion was going to be a minimal release mechanism. Corrosion was the primary release mechanism. So we incorporated that in, basically through a series of rate constants that described the release of tritium from the beryllium. We had spatially and temporally varying infiltration rate and waste and placement. So over time, you would put blocks of waste in here, and these corresponded to grid blocks in the tetrad model, and that would provide a flux over time, and with different container rates. It actually got quite complicated, and really the bookkeeping was very difficult, I think. Okay, so this is roughly our dust model, and the time-dependent container lifetimes. Actually, that didn't turn out to be a big factor. We spent a lot of time getting Gaussian distributions on how long a container lasts, but it didn't turn out to be a big factor in it, especially for the transuranics that sorbed in the soil. It didn't matter whether the container lasts 10 years or 100 years. It really didn't matter. And we calibrated it to the carbon tetrachloride in the Vadose zone and nitrate. This was, actually it's too bad Marty isn't here because this is his favorite example to give about performance assessment modeling. Because in our 94 PA we assume no partitioning between two-phase transport for carbon-14. So in this particular application we did, because it was one of our primary dose drivers, and that is carbon-14 partitioning into CO2, migrating to the surface, it's gone, and a fraction of it going down with the pore water into the aquifer. So you're looking at the difference in concentration here with gas phase partitioning and without, one of the sensitivity cases we ran. And you can see it's a huge difference, and so suddenly carbon-14 now is not a big dose driver. As in our initial PA in 94, it was the biggest dose driver. Okay, yeah, that we used a column experiment to come up with the parameters. So this is a case of we used a simple model, boom, identified the key radionuclide or the process that we had to look in more closely. And that's, we had that feedback then, did the groundwork, the experimental work, and then the modeling work. And now we have pretty good, carbon-14 is not an issue. Here's the CERCLA risk assessment modeling results. Here the key thing is carbon tetrachloride is driving the risk here in terms of a risk contributor. The next is the Tec-99, and Tec-99 is the key radionuclide in the CERCLA risk assessment. Keep in mind we're, for the PA we have essentially the same source term, essentially the same modeling, and we get slightly different results because of a different assessment question. And there's the rest of them. Okay, we had different assumptions and endpoints, and so we could not use really the model directly. We had a different set, actually, of radionuclides we needed to consider, slightly different set. What we could use, we used. So we took the dust simulations and some of the radionuclides, well, some we had to do from scratch, tritium, because they did not do tritium in the RIFS. Then we abstracted the model to improve computational time, because we were going to do Monte Carlo uncertainty, and we had a number of other things. Jeff, what was the runtime on those tetrad? Oh, come on. A week or two run times, just give you an idea. So we included Monte Carlo uncertainty. Obviously, we weren't going to do Monte Carlo uncertainty with a 2-week run time. Here's some of the model abstraction. The reviewers got very confused with this graph because this green line here is the source input, and that actually corresponds to the right axis, which is cut off here. The red line here is what tetrad predicts, and that is an integrated flux across the bottom of the domain to the aquifer. Our 1D model abstractions shown here. Now, for all practical purposes, I'd say that's pretty close. Someone say, well, no, look at that, it's slightly higher. That is a linear scale, by the way. Well, consider the overall uncertainty in our model. And here is the concentration in the aquifer, and that concentration is, tetrad was 3-dimensional, a fully 3D model. So what we looked at was looking at a 100-meter buffer, pick the maximum concentration in the aquifer, and plot that as a function of time. So that's what's shown here. So it was very important that when we abstracted our model, that we identified what are we going to calibrate to, what are we going to compare. So this showed actually we had pretty good comparison here. And here's the PA results. This is a lot of data, but the big thing is now our big dose driver is tritium during the institutional control period, but actually our compliance, our point of compliance is not at this site during the institutional control period. But now chlorine-36 shows up. Go back. Yeah, come on, go back. Look. We had this pretty much the same concentration. Why is chlorine-36 the driver? Chlorine-36 is the driver because we have an all-pathway scenario. They only computed groundwater ingestion risk, not following it through the food chain. When you follow it through the food chain, because chlorine-36 has a high concentration ratio, now it becomes the risk driver. So chlorine-36 becomes the big risk driver in the performance assessment, whereas in the RCRA surplus assessment, the radionuclide was Tech 99. We also did allow the model abstraction allowed us to do Monte Carlo uncertainty. I think certainly this was done. I think, Greg, you were talking about how you linked all these models together. Yes, we use scripts too, Perl scripts, extensively, and I really don't have any complaint with them. But they're basically used to wrap everything. We use a Perl script to wrap the code, and we can integrate any number of different codes into this. For example, run a source term model, do our parameter sampling, run a source term model, integrate that with rewrite the the Vedo zone model with the results from that, and so on. We did have data to at least compare to, actually going back, 2000, they really started monitoring. And I think this is important to put a perspective on how well can we really model. This is a tritium, and we're way off. There are predictions up here, and we have measurements down here. Now, the problem is trying to identify what's the problem here. Because when you run the uncertainty analysis with any kind of estimate of at least making an estimate of the uncertainty in the inventory comes out to be one of the biggest factors in all of it. And frankly, we don't know the inventory that well, let alone the inventory or the release mechanisms. But this hopefully provides some confidence. I think we've overestimated it. Here's the carbon-14. This is from tetrad, and that is a linear scale. Keep in mind, these values all here are non-detects. And this is the abstracted model for chlorine-36. At least we got somewhat the trend right. This is, of course, log scale now. And here's a lot of non-detects. So I think it's important to have that feedback when you do have measurements, to always be looking at that, because this is the bottom line. This is what you want your model to predict. So in general, our performance assessments, at least for the RWMC, we built upon the knowledge gained during the RIFS process. However, different assessment endpoints require different modeling approaches. And in addition, we also had different assumptions regarding how we're going to close the site in terms of cap longevity and what kind of cap was going to be put on it. So we could look at a number of different cases with our abstracted model. Okay, the second is the WAG3 RIFS and the ICDF performance assessment. The WAG3 addressed these nuclides, strontium-90, Tech-99, I-129, and nitrate from leaks in the waste transfer lines at the Intech site. And Idaho ICDF PA is located in that general vicinity, and we just, it basically is a lined CERCLA facility that receives contaminated soils, contain both radionuclides and chemicals. These are Intech's up here. Here's Intech. The main part of WAG-3 was up here, up in the northern part of it. ICDF is down here. This is a line facility with a leachate collection system. So the WAG-3 RIFS had 3D tetrad model with geostatistical interpretation of the sedimentary interbed structure, and the detailed part of that was probably the geochemical modeling required for the CPP 31 release. And Tough React was used there. And they also had 50 years of water level data to compare to and calibrate with. There's our geostatistical model of the interbed structure. And these are actually calibration to concentrations in perched water. Perched water is important in terms of our ICDF performance assessment because it can enhance, obviously, the vadose zone transit time. But our perched ICDF is down here and outside of the zone of the perched water. Here's a current extent of the perched water. And this is up at TRA. These are percolation ponds, and it has an influence on the perched water. Big conclusion with the detailed modeling there was the anthropogenic and natural infiltration from the Big Lost River are the driving forces in the northern half of Intech. And strontium-90, typically not a groundwater problem, showed up to be a strong groundwater problem, a real problem because of the geochemistry of the actual release and the large amount of liquid waste that was released. Other important radionuclides was Tech-99 and I-129. And one of the big conclusions, in the absence of anthropogenic water and influence from the Big Lost River, infiltration was shown to be essentially gravity-driven, one-dimensional flow. And so we've used, this basically confirms our earlier assumptions about under natural conditions we have a one-dimensional flow system. That model was eventually also abstracted into a series of response functions and used for a high-level waste EIS. Here's the ICDF. It's the line facility has a leachate collection system. Water, basically the waste is dirt, and it is watered down. The leachate is collected and put to these evaporation ponds. And our hydrologic model for the ICDF PA was based on the WAG-3 modeling. So essentially we take this geostatistical model, because it's outside the influence of the Big Lost River and the perched water, and we've reduced it to a 1D column. One of the key assumptions, and this probably is going to come up some more, is that our liner fails before the engineered cover. If the liner doesn't fail, I still have to do that analysis, which may require more additional work. But this basically is our conceptual model, a 1D system with time-varying infiltration rates. It's currently under a review. The new model incorporates some of the information we got from the WAG-3 RIFS, and we included higher infiltration and revised inventory estimates. So the WAG-3 was essentially a retrospective analysis, and the ICDF is almost purely a prospective analysis. We don't have data to calibrate it to in that sense in terms of contaminant transport. We have incorporated the data like how much water are they pumping from the leachate collection system. That gives us a very good idea of how much water is collected, how much water is infiltrating from that system. But the main thing is that the WAG3 RIFS supported the assumptions we used in the ICDF. And the last one is the WAG10 groundwater model and RWMC composite analysis. So WAG10 really includes the whole Snake River Plain aquifer, which currently contains plumes of tritium and iodine, Tech-99. And the WAG10 model, we're going to apply it to the composite analysis. Here's the modeling domain, fairly large area. Here's a big lost river. So we have recharge, boundary conditions set. This was done with ModFlow, MT3D, and calibrated to levels at Intec. Calibrated to the Intec tritium plume. This was an important part of this study was the flow paths. What it says here, here's Intec, is hydrologically separated from the RWMC, but RTC, or what they call the Advanced Test Reactor Area, Reactor Test Complex, is connected right here. So in terms of a composite analysis, these are the sites we need to consider. These two sites are in line. A source here has minimal interaction with that at the RWMC. The WAG10 model was abstracted into a response surface model, and this was what was used to do most of the production runs for the RIFS. And so the response surface model basically takes a response from a steady state flow field and predicts what the response at a given source node and at a given receptor node. And we implemented this in a Microsoft Excel database just to store the data and a DLL to actually do the computations. This was one of the problems we found is the discretization problem. This is the tetrad model of the saturated zone underneath the RWMC. I talked about this low flow zone. The problem is that when we put it in the WAG10 model, we didn't have the discretization to carry it to the extent that it was in the tetrad model. So when we look at the concentrations predicted by the WAG10 model and those predicted by the tetrad model, actually the WAG10 model's here, it's quite a bit different just because there's a lot more water flowing through the WAG10 model compared to the tetrad model. We did not have the discretization in this area to represent it. So it's certainly useful for defining sites that may interact with one another, but spatial resolution of the near field may be inadequate for the overall effectiveness of it. So in conclusion, the assessment question for circular risk assessment and low-level waste performance assessment are somewhat different. Performance assessment is essentially a prospective analysis. Circular modeling is retrospective and prospective. So really there's different modeling approaches should apply. Historical monitoring has certainly allowed for model calibration for the circular assessments. For prospective low-level waste, there's really, in terms of long-term performance, we don't have the data to calibrate or to validate our model. And certainly at the INEL, our low-level waste performance assessments have benefited from the detailed characterization work performed for circular risk assessments. All right, now some considerations for ASCM. I'm sorry I'm not as detailed as Greg got, very detailed. But I asked, when designing this model, to consider objective and assessment questions of a performance assessment in contrast with an RIFS. I've seen a number, at least some of the people I'm working with at the INEL, Roloff, Van de Stieg, who really works in this arena, has a very different idea of modeling than I do working in this arena. And I think if you're to make this useful, you need to consider both aspects. Complex models require substantially more characterization data. Have to consider, is it practical to collect these data on the scale necessary to parameterize a large model? This, well, this feeds into here, and I'll go to that, elaborate on that a little more. Greater model complexity does not always result in a better model. Sometimes it's worse. In both of these, the source term can drive the problem. And I don't mean to be flippant here, but no source, no problem. So if you can understand the fluxes coming out of your source and feel fairly confident in that, it may behoove us to spend more time working on this problem, like what the cementitious barrier issue, get that, than spending a lot of time worrying about what happens once it gets out. Just something to think about, because this is something that you can actually probably go out and measure fairly easily. This stuff is right there. You've got your vault right there. It's a lot more accessible than, for our case, 400 feet down in solid basalt. That's hard to parameterize that when you can only poke a little hole and you don't even know if you've characterized it correctly, because 10 feet over it might be completely different. And it's very expensive to poke holes through solid basalt. This reiterates what Dave Esch said. I didn't plagiarize him. I wrote this independently. But models don't make decisions and should not make decisions. Humans make decisions. And so they should provide the knowledge and understanding to decision makers so they can make informed decisions. They have to make the decision. Okay, that's it.
Okay, thank you, Art. Questions?
Ralph Perona with Neptune and Company. So I was really got me thinking here about the circular versus performance assessment modeling domains, because I work in both areas also. And looking out at future cancer risk or systemic toxicity or future radiation dose, I mean, in general, I struggle with a basis for differentiating the modeling. It seems to me in some sense that in either case, you're essentially looking at dose or risk to individuals who are unaware of the disposal facility. They're going about their lives. You have a set of exposure pathways under some set of scenarios. And whether it's a chemical toxicant or radionuclide or mixed waste, in some sense, the exposure model is independent of the type of contaminant. I wonder if you could speak to that a little bit, because I got the feeling looking at the chlorine and Tech 99 that you had different exposure models for CERCLA versus PA. Yeah, there were different exposure models. The CERCLA looked at groundwater ingestion risk, just groundwater. The PA has an all-pathway scenario where the water is not only ingested directly, but also used to irrigate crops and water livestock and the whole 9 yards. And so what happened, why chlorine 36 showed up, is because chlorine 36 has a huge concentration ratio. So it concentrates in the vegetation when you irrigate with it. So you get a proportionally higher dose. Why were those pathways not important?
Because they didn't they didn't look at using the water for irrigation and and growing crops and all that. They looked at the risk from living on the surface and directly ingesting this and having radionuclides that may come from the waste disposal pit onto the surface, but they didn't look at that. So,
Why not? I mean, why didn't they look at that?
Coffee beans, yeah, it might have been the.
I wonder were there different individuals who kind of reached concurrence on what is and is not a
Yeah.
domain of the modeling?
Yeah, that's different individual, different arenas there. You know, there. What's that?
Another source of uncertainty. You said something wrong.
But in both cases, the chlorine is well below the standard.
In both cases, the chlorine was well below the standard. That's another point, is that in both cases, the chlorine did not approach MCL or approach our dose limit in that sense. The other aspect to that, though, was this cancer, was the concentration curve. Remember, the cancer risk is computed over a integrated 30-year lifetime, I think. Yeah, 30 year. So if you have a large pulse that occurs over your 30-year period, you're going to get really different results if you're looking at the maximum. The dose is based on a maximum 1 year annual dose, not averaged over 30 years.
Although some of the dose coefficients assume more than 1 year exposure, so it's a little.
No, they don't. No, that committed. Well, let's not make a dose. I'll talk to you later about it.
Without going back to the microphone, can you go back to the slide you had that was that all pathways, and it showed the chlorine 36 way back. It's for your case 1.
Yeah, I remember.
Because
This thing isn't very fast. Here we go.
there, okay. What I'm noticing is the blue triangles, U235 at the very end, that's becoming a driver at the end.
Yes.
And
And you know why it's becoming a driver? This is another issue here. It's not from.
Can you repeat the question?
Yeah, repeat it. So it's on the
it's more of a comment. I'm commenting that U235 is a risk driver at the end, so I'm kind of asking that you talk about that a little.
Okay, talk about the U235 as a risk driver at the end of the out here beyond 10,000 years. It's really, technically it's not U235. It is PA231. And what happens, see, this is the way I personally like to do it, is I attribute the dose to U235, even though it's coming from PA231, a daughter is attributed to the parent U235. You know why? What?
But you have PA231 in the graph.
That is from a disposed PA231. See, if you're going to establish waste acceptance criteria, you have to establish it in terms of what you dispose, not what's going to grow in. And so I think this is extremely important in terms of when you do your reporting, you attribute the dose to the parent.
And so it's mobility, is that what's?
Yeah, PA2, yeah, well, it's dose coefficient,
right, but the timing.
timing.
Why it grows in, why it appears so late.
Oh, it appears so late because it takes a fairly long time for it to grow in.
Oh, for the growth.
Yeah.
I see.
Right.
You mentioned about the model calibration, the circular model versus performance model. In your performance model, because you don't have enough data, that you mentioned that there's no enough monitoring data, but if you have enough monitoring data for the circular model, like Hanford, we have decades of data for groundwater contamination from chemicals and like that. We may not have data for radionuclides under the tank farms or something like that to calibrate these things. But if you use those data that you have for the chemicals and you really calibrate well and these things, I don't think there will be enough, there should be big uncertainty as far as the model is concerned. To compute performance assessment for the radionuclides or whatever.
So what you're saying is you can use natural, well, the chemical
Yeah.
data to provide basically support for your performance assessment,
right.
flow, and transport. Yes, I agree with that, but I guess I'm being more exact than that. Ultimately, when you do any prospective assessment, you can't truly validate your model because what you're predicting has not occurred, right? The only way you can truly validate it is wait 200 years or however long. That's kind of what I'm saying.
Okay.
But certainly you would want to use whatever information you have right available, including natural analogs for that matter,
That's right. Okay.
to calibrate your flow and transport model.